Good morning, good afternoon, or good evening. We are now on question 10 of the Step 3 2024 paper and our second mechanics question. This particular question looks incredibly daunting. It's an entire page worth of descriptions. There are quite a few show that's in the question, and it's all talking about sliding versus toppling. So we need to have the ideas of moments and whether the moments are going to balance, and then of course for the sliding condition whether the forces balance. As with every mechanics question, the most important first stage is drawing, oops, don't know why I'm all the way over there, is drawing a accurate large picture which has all the information, doesn't make any extra assumptions, and can be used throughout the question to pick out the relevant things at each time. So here we have a cube of uniform density rho placed on a horizontal plane, and a second cube is placed on top of it. So I have my horizontal plane, I have one cube on it, and a second is being placed on top. I'm not going to put it there yet because it could be in lots of different places. It could be off to the side or placed centrally. The lower cube has side lengths of 1. So if it's got side lengths of 1, it's got a volume of 1. So its mass is just rho kilograms. And the upper cube has side lengths of A. So that'll be A cubed rho for its mass. The central mass of the upper cube is vertically above the central mass of the lower cube. Okay, so that does mean that our upper cube is placed symmetrically on top with a mass of A cubed rho. We've got side lengths of 1, side lengths of A. The centre mass is vertically above and all the edges of the upper cube are parallel to the corresponding edges of the lower cube. Okay, so it's all placed perfectly, symmetrically, and in line with everything. The contact between the two cubes and between the lower cube and the plane are all rough. So we have a coefficient of friction being involved everywhere. The midpoint of the base of the upper cube is X. And the midpoint of the base of the lower cube is Y. So that point there is what I'm calling X. That point there is what I'm calling Y. A horizontal force P is exerted perpendicular to the vertical face of the upper cube. A horizontal force perpendicular to one of the vertical faces of the upper cube, halfway between the two vertical edges. So it's symmetrically in a kind of a depth of the picture. Really, this whole picture, I've got a cube with the second cube on top, but I'm looking at all of this from one angle, making it basically a 2D picture rather than a 3D. So that statement is saying, yes, you can make it look like a 2D. It's symmetric in the depth direction. And a distance h above the lower edge of this face. So this distance here is h, and then it's insisted that h is less than a, so it's not floating off the top of that cube. Okay, so before I look to see what I actually want to do with the problem, I would like to add in all the other forces that are involved, and there are going to be quite a few extra forces. So we're going to have a mass of the upper of A cubed rho G. We're going to have a reaction force, and depending on the situation will depend where this reaction force goes. I'm actually going to automatically put it on this edge here, because if this is going to topple, it's going to topple this way. And if it's not toppling, then the R can be placed basically anywhere around. But I'm kind of pre-imagining a pivot happening. and that I'm going to call RU for the reaction force of the upper cube. Now for the upper cube, there are no more forces. Oh yes, there is. There's the frictional force. So because we're being pushed off to the right, you're going to have a frictional force going off to the left, which I shouldn't automatically make as mu r, because I don't know whether we're at the point of slipping, but this F sub u for the upper cube will probably be mu r later on. And then for my lower cube, let's look at the forces I have. I'm going to have the mass creating a weight, a PG force. We have the equal and opposite of the frictional force. So on the lower, and I think I actually want to do all these forces in a different colour to make it just that little bit more obvious in when I come to look at these separately later on. So I'm going to have this frictional force as an equal and opposite there. I'm going to have a equal and opposite for the reaction force. We're going to have the mass of the lower. We're going to have a frictional force on the ground, which is now going to be pointing opposite to the equal and opposite frictional force on the other section. So this is going to be F of the lower. So I'm going to call this FL, friction of the lower. And then the reaction force. Now, where would I quite like to put the reaction force? Where is this pivot? If this is going to be pushed over, then it's likely to be rotating round on that axis. So I'm going to put a reaction force here, reaction force on the lower. And I could, if I want to, start to evaluate some of these. So both the reaction forces, this reaction force up here has to match its matching vertical. This P force will have to match this force if things are all in equilibrium. And similarly for the lower, although there are more forces on the lower object to worry about. So now let's actually start looking at the question. So part I, show that if the two cubes remain in equilibrium, so now all the forces balance, all the moments, balance, the normal reaction of the plane on the lower cube, which is this RL, which I've labelled, acts at a point which is at distance from Y. Okay, so it's saying where is this reaction force? So really when I drew this, we're asking where is it positioned? At what distance is it positioned from the Y? And find a similar expression for the distance from X of the point at which the normal reaction of the lower cube on the upper cube acts. So then similarly for this RU, that's going to be somewhere over here, which already goes against one of the things I've said, that if we're not toppling, we're in contact on all the surface, it doesn't really matter where that force is actually acting. It's a bit odd, but we'll go with it for now. So we want to try and find the normal reaction force on the lower cube acts at a point which is at that distance. So do I want to think about forces or do I want to think about moments? it's talking about distances, which kind of implies I want to think about moments, because forces themselves don't include a distance otherwise. And by the way it's worded, it looks like I want to use the entire 2-cube system altogether. So let's look at these 2 cubes together, and well, let's take some moments. Let's take moments around the point Y, because I want to know the distance from the point Y. And if I take moments around there of the entire system, well, what forces do I have? Things to notice, these 2 forces are equal and opposite, so cancel out, and these 2 forces are equal and opposite, and really I should draw this arrow directly with the other one to kind of match up their things. So I don't need to worry about that, don't need to worry about those. So the only ones I do need to worry about are the friction along the bottom, which I don't because it goes through the pivot. So the only forces I actually care about are the P force, and I don't even need to do the 2 weights either. So we have that, and if I call this distance for a moment D, we're going to have the moment caused by the pushing force at the top at a distance of 1 plus h, because of course the height of the whole object is 1, so that's a distance of 1 plus h away from Y, and that's going to be equal to RL times D. So we need this force RL. If I take up equals down, again ignoring the RU terms, we have that the RL is A cubed rho G plus rho G, or if I factor it, which means that this D is P1 plus over rho G1 plus A cubed, which is exactly what we wanted. So actually follows from the picture near instantly. So that's where this reaction force is actually acting. So now we want to find a similar thing, but for the top cube. So if we do the upper only, and I'm actually going to do them in a slightly different order. So if I look at the upper only, so I'm only looking at the blue arrows in my picture, and this time I'm wanting to find the distance there. Up equals down says that the reaction force U is equal to A cubed rho G, and if I take moments around X, the FU force, the frictional force, is irrelevant. So that leaves the P force times its distance equaling the thing that I care about, which I shouldn't really call the same letter again, so I'll call that E. Times by the RU, so therefore E is PH over A cubed rho G. Okay, so that's part I done. The force P now gradually increases from 0. So we're making each of these forces larger and larger and larger, the P force to be as larger and larger and larger, which will slowly make the D force, the D distance increase, and the E distance increase. And this is an interesting idea, because as soon as this D distance here gets bigger than 1, the reaction force is now on the outside of the diagram. Well, that's exactly the condition that this is toppling. And similarly, no, not less than 1, less than a half. As soon as it gets bigger than a half, sorry. So as soon as this is greater than a half, we're toppling, and as soon as this is greater than a over 2, we're toppling. May be relevant later in the question. But what does part 2 actually want? Show that if neither cube topples, equilibrium will be broken by slipping of the upper cube on the lower, not by slipping of the lower cube on the ground. So we want to show that the condition to not slip is easier to break on the upper than on the lower. So let's do those two calculations. So we slip upper on lower if the frictional force is greater than mu r, i.e. this frictional force, and we have a left equals right here. So we're going to slip if, well, really, we're slipping if P is greater than the frictional force, which once we start slipping, friction we'll say is equal to mu r. But if I do up equals down on this picture, we have again that Ru is a cubed rho g. So we're slipping on the upper as soon as the P force gets greater than mu a cubed rho g. And now we need to do a similar thing for the lower. So slip lower on ground. And again, I think we want to tackle this you're looking at the entire object as a whole. So together, again, looking vertically, we have that the RL is rho g 1 plus a cubed. And so we slip if the P force, now I'm looking at combining all of the arrows together, but I'm ignoring the RU and the friction on U. So I'm only left, with P is greater than FL, which is going to be mu RL, which is rho G, mu rho G 1 plus alpha cubed, which is a bigger condition. So as mu a cubed rho G is smaller than mu rho G 1 plus a cubed, the top cube slips before the lower. So you've shown there that this condition is easier to achieve than this condition. So the first one that's going to break down is we slip on the top rather than on the lower. Okay, part 3. Show that if A equals 1, so that's now saying the two cubes are identical in size, and things to notice is this will then become just over 2 rho g. This will just be over rho g. Then equilibrium will be broken by the slipping of the upper cube if that, and toppling of the lower and upper together if that. Okay, so let's kind of break down what the possibilities are. So we're now setting A to be 1. And we're going to have lots of different possibilities. So we are going to slip if P is greater than mu, I don't need the A anymore, rho G, so that I've just stolen from here. We're going to, well, there's more than just, there's lots of different toppling cases that we could have. We could have the top block. We could have the top block toppling, or around that point, or we could have the bottom block toppling. So let's put some conditions on each of those. So the top topples, if this thing we called E earlier, if this E was greater than a half, so that's P H over, again, I don't need the A because in this case the A is just 1. Rho G is greater than a half. IP is greater than rho G over 2H. So there's another condition. And then the entire topples, which is the same as saying just the bottom box topples, providing the top hasn't already toppled. If the thing that we call D is greater than a half, so that was P 1 plus H over 2 rho G is greater than a half, which is the condition that P is greater than, the 2's now cancels, this is rho G over 1 plus H. So, what are the different situations for each of these? Well, firstly, these second two look very, very similar. So let's see what happens with those. So as H has to be smaller, we said that H has to be smaller than A, so H has to be less than 1. That means that it's divided by a smaller thing here. So which one of these happens first? Sorry, no, the other way around. This thing is smaller, so that fraction is bigger. So as H is bigger than 1, this rho G 1 plus H is smaller. So toppling of the entire system happens before the top topples. So we're never going to have the case where P gets to whatever this fraction is, because that's a bigger fraction. This would have already broken the setup first. So now we want to compare the two. So, and if you do look at what the answer we're looking for, you won't be surprised here. So now we want to compare mu rho G and the other. So how do I want to say this? So we'll slip first if the slip condition is easier to achieve than the topple condition. So I'll slip first when mu 1 plus H is less than 1. And I'm checking, show that if A equals 1, the equilibrium will be broken by slipping. If that, perfect. And we'll topple first if the toppling condition is easier than the slipping condition. which is exactly the opposite way round. So this thing is greater than 1. Lovely. And that's exactly what part 3 wanted of us. Now, in part 4, show that in the situation where a is less than 1 and that nonsense holds and no slipping, equilibrium will be broken by toppling of the upper cube. Okay, so that's quite a lot to take in. First, we don't need to worry about slipping. So we're only worrying about the 2 toppling cases, and we're going to try and use that condition to show that the toppling condition for the upper cube is easier than the toppling condition for the lower cube. So let's pull what we have together. So the top topples, if the E that we had is greater than A over 2, yep, this E here, as soon as this gets outside of that upper cube, we are going to topple. And that E's expression was pH over A cubed. So that's pH over A cubed rho G is greater than A over 2, or equivalently, P is greater than A to the 4 rho G over 2H. And that to me is quite pleasing straight away because it has the A to the power 4. I was a little worried where an A to the power 4 may come from. And then the entire topples, or I should now say lower, because we've got the case that the top may topple first. The lower topples, if this D is greater than a half, and that is that P 1 plus H over the 1 plus A cubed rho G is greater than a half, which is saying that P needs to be greater than 1 plus A cubed rho G over 2 1 plus H. We want to show that in the situation where that and that no slipping goes, equilibrium will be broken by the toppling of the upper cube. So we want to basically compare these two conditions again and see which one is easier. I'm trying to consider the best way to tackle it. So I think I might, we're in mechanics, so I'm going to be a bit fudgy with some of my implications here. So I'm going to say with the upper topples first, if that's toppling condition, and I can say if and only if, and then that covers my implications. If that's toppling condition is easier than the other toppling condition, I don't need to worry too much about the fact that I'm dealing with inequalities. Everything's positive here. So I can cancel the PGs. I'm going to multiply up. I can cancel the 2's as well. So 1 plus HA to the 4 has to be less than H 1 plus A cubed. The rho G's have cancelled, the 2's have cancelled, and basically now I want to rearrange this to get A to the 4 equals, so I can say this is A to the 4 is less than H plus HA cubed minus the HA4, which was on the left, which I don't want there anymore. So A to the 4, and I should put in the if and only if conditions on each of these lines. So that's if and only if, and the way they've written it is they factored out the H1 plus, they factor out the A cubed 1 minus A, which is exactly is the given condition. Okay, perfect. So thus the upper tuples. So we basically put the conditions on, found out which was easier, and went from there. Finally, part 5. Show, by considering a equals a half and choosing h and mu, that the situation in part 4 can in fact occur. So we're forcing ourselves to be a equals a half. Now the situation in part 4 is there is no slipping. So we need to recall that let's deal with the condition part 4 first. So IV implies that a half to the power of 4, which is 1 over 16, has to be less than h. 1 plus an eighth times a half, which is, that's a 16th, so that's 17 over 16h. So h has to be greater than 1 over 17. Okay, so we still haven't picked h, but basically anything bigger than 1 over 17 will ensure that the top topples before the bottom topples. Now we also need the slipping condition. So we're going to slip. So we slip when P is greater than mu rho G, and we topple when P is greater than the upper topples. Which one are we doing? The top topples. So I'm looking at this thing here. So the top topples when, well, a to the 4th is 1 over 16, so it's going to be over 32h rho G. So for IV to occur, we want to be toppling before we slide, so we require the toppling condition to be easier than the slipping condition, which is equivalent to saying that 1/32h mu. So now I need to pick h and mu to make that work. So then let's pick, well, if h needs to be bigger than 1 over 17, let's go for 1 over 8, and mu to be a half. So that condition does hold. 32 times an eighth times a half is 2. Then the toppling happens before sliding, as in part 4. So we actually had a lot of choice on how we pick these. This condition is basically saying that the h and the mu have to be big enough that their product is bigger than 1 over 32. And this condition feels very weak. Only being bigger than 1 over 17 seems really weak, considering the fact that we've got a cube that's half the size. We need that to be really, really low down, which kind of does make mechanical sense. As soon as this gets at any height, given any oomph above the base, you're going to rotate here before you rotate here. And then we just needed to make sure that the mu and the H behaved well enough together. That question turned out to be relatively nice after we drew that picture, and most of those show that just fell out quite nicely. Rest of this playlist then has the rest of the questions from this paper, and hopefully they are equally useful to you. And good luck.